Hello, I'm Keegan Williams, and this is my Physics 2211 lab on a falling Slinky. So first, in order to understand this lab, we have to know some fundamental physics principles, including the momentum principle, which states that an object's momentum will change over time when a net force is present. The momentum principle can be rearranged to get the position update and velocity update equations, which will be implemented in the GlowScript codes to find the predicted position of the object after a time t in order to better understand the net forces on the system. The turbulent drag equation will be the drag force on an object is opposite the motion and proportional to the square of the object's speed. And below you can see the equations that we're going to be using. So the purpose of this lab is to see how the momentum principle holds for a falling slinky, where the bottom part of the slinky stays stationary as it falls until the top begins to compress against the bottom. By using a computer model, we can effectively make a model that mimics the motion of the slinky in the provided video. Through this lab, we will see that the model is an effective indicator of the motion at the bottom of the slinky as the spring compresses. This is supported by how the motion of the observed slinky and the model slinky are very similar. And here's a tracker video which shows the falling slinky in slow motion. So in order to better understand the system, we can draw a free body diagram. So the system for this experiment would be the bottom of the slinky object, and everything else would be the surroundings, which includes the air and the ground. And this free body diagram specifically represents the net forces acting during the first half of the motion. So although the video was borrowed or pre-recorded, to perform this experiment we would first have to obtain a slinky and measure the distance from which the slinky was being dropped. Additionally, we would need to measure the mass of the slinky and the displacement of the slinky as measured from the bottom. After obtaining a video, we uploaded it to Tracker, where we hand-placed coordinates over the position of the bottom part of the slinky as the mass fell. Then, using Tracker and GlowScript, we compared our experimental data to a computer model that assumes ideal conditions. So, for initial conditions and how we implemented them, in our system we found the mass, spring length, and displacement from the provided video, along with reasonable approximations. The displacement was calculated using the distance the bottom traveled to the ground. This distance was calibrated using the heights of the men in the video. Additionally, we assumed that the initial velocity was 0 meters per second. So for the iterations of the bottom part of the slinky, before the bottom falls, the net force on the bottom of the slinky is 0, which means that the tension force in the slinky is equal to the magnitude to the force of gravity. After the bottom begins to fall, it starts to accelerate as one object. Tension force is unincluded since it's equal to 0. However, drag force is now included. In this part of the iteration, the net force is equal to the drag force plus the wave force. So here's our GlowScript results, which show the position of the slinky bottom over time. And here's the difference between our observed and model position versus time graphs, and you can see that they're very similar. So overall, the differences between the experimental and predicted motion of the falling slinky are very similar, as they only differ in travel path when there is a net force on the bottom of the slinky. This means that on whole, our model was an effective indicator of the motion of the slinky. So for this lab, possible sources of error would include the slinky being non-ideal as it wears over time, the descriptions provided in the video being inaccurate, the hand placement of the positions in Tracker, which may cause inaccuracies over time, and initial conditions like drag coefficient and delta t, which are derived from trial and error. So some follow-up questions include, why does the slinky stay temporarily stationary when falling? So from the perspective of the bottom part of the slinky, there are only two forces acting upon it, tension force and weight force. Since the tension force is equal and opposite to the weight force, the net force for this part of the iteration is 0, so it'll stay at rest. Once the top is close enough that the tension force goes to 0, the top and the bottom of the slinky can be treated as one system. So at this point, the only forces now acting on the slinky are weight force and drag force. Since these two forces do not sum to 0, there is a net force present for this part of the iteration. So, in conclusion, this lab was valuable for analyzing and understanding how forces interact on an object in air to suspend it in circumstances where the object does not have a contact force like normal force exerted on it. Using a computer model, we effectively predicted the motion of the bottom half of the slinky system based on the initial conditions provided in the video. Our results showed that the model closely matched our experimental data, suggesting that while the predicted position of the object was slightly different over the course of the motion, the net displacement was very similar to what was seen in the experiment. Overall, these findings reinforce the momentum principle, which states that an object's momentum will change over time when a net force is present. Thank you.